right, so there are many things I want to tell you today, maybe too many, so if it goes over, just stop me. Okay, so let me recall a little bit the context we introduced last time. So we are starting with Hilbert space. And for now, we look at the simple case where the dimension is finite. So we introduced the space of observables. It's called A, and these are operators on H. And the only requirement is that they must be self-adjoint. So we also introduced the space of what is called states. What was it? S. So these are also endomorphisms of H, but here there are many more conditions. So they are also self-adjoint, they are non-negative, and they are of trace 1. Now there is something that I forgot to tell you last time, and maybe let's spend 5-10 minutes and I tell you some small story. So let's say we have a vector in H of length 1. Then recall that last time we defined a projector on a one-dimensional line, on a one-dimensional subspace, which is spanned by this vector. And this projector, it works like that. So it's given by the Hermitian product of the vector with the generator times the generator, right? So recall that the Hermitian product is linear in the second term and anti-linear in the first term. Now, so let me also recall that such projectors, they are by definition, so orthogonal projections like that are self-adjoint. It's easy to verify that they are non-negative. And the trace is equal to 1, right? Because there is one eigenvalue equal to 1, and all the other eigenvalues are equal to 0, right? So in fact, we have two interpretations for such projectors. We can think that they are observables, but we can also think that they are states. So we already discussed as a state so they define very special states which are called pure states. But now maybe one question which remains, what do they mean as observables? So probably those of you who already started quantum mechanics as a physics course, you probably would have some idea. So what's the opinion of the experts? What are those observables, right? So the states correspond to length 1 vectors. So that's something that we learned last time, or that's something that we learned in quantum mechanics. But now, what are they as observables? What are the words? Let's say, of course, the mathematical formalism defines for us those observables. Observables are self-adjoint operators. Orthogonal projections are self-adjoint operators. But what do they measure? Right? Because an observable, you imagine something like a physical quantity. I don't know, mass, velocity, position, something. So what do those things measure? So this is in some way a question about the dictionary, the words that we should use when connecting from the math formalism to the, so to say, physics world. So the experts in quantum mechanics, your opinion? Say it. So what's the meaning of this observable? So I'll ask this question in 1 minute, so please be prepared. So let me recall that we can associate, so say we take this observable, Pu, and we associate to it a probability density. So we consider, where did we write the observable? I think the observable we were writing down here, and no, I think we were writing it. And we consider it in the pure state. So that's the state, that's the observable, right? So there will be a probability density here. So this probability density will be a linear combination of delta functions which correspond to eigenvalues. So what are the eigenvalues of this guy? So they are 1 and 0, right? So there will be a delta of lambda minus 1 plus the coefficient delta of lambda. So in total, so that's 0 and that's 1, and we can measure one of those. And here there will be probabilities. So what are those probabilities? Here, let me recall, the probability is just a trace of a product of the observable times the state. And here will be a probability which is 1 minus this guy. And if you look at it, what will it be? So I think we should take 1 minus Pu times Pv. Right? So if you follow the rules, that's what will happen. But let's focus on this one. So let me ask again, what does it measure, this observable? So the observable Pu. I think it measures a very simple thing, whether the system is in the state defined by this projection. So this projection has a double role. It's an observable and a state. And the observable measures whether we are in the state defined by the same projection. So physics interpretation to the observable, which is given by the projection, measures, or let me take it in quotation marks, whatever this word means in physics. Whether the system is in the state Pu. You see that that's a funny thing that we are now using the same projection, right? It's the same orthogonal projection on the same one-dimensional space, but we're using it in two capacities. So why are you, am I talking about it? Because from time to time, in quantum mechanics and also in mathematical quantum mechanics, you're asked, so what's the probability that the state is that the system is in a given state? And typically the state is defined as a pure state, defined by some vector. Right? So this is a linguistical question, right? So to it should correspond some mathematical question. So now I'm telling you what people actually want to know. So they want to know what's the expectation value of this observable in a given state. The state may be a pure state or not a pure state, whatever you want. But the observable should be this one-dimensional projection. So maybe, I think we already done this calculation maybe in less detail last time. However, let me compute this trace. So there is a trace of Pu times Pv. U and V are two unit vectors in a Hilbert space, and we are computing the trace of the product of these two projections. So let me do the following. Let me use an orthonormal basis in H, and I denote it by EI, sum from 1 to n. So then we know what is this trace. So this trace is sum over I from 1 to n, EI, and here Pu, Pv, EI. Right? That's one of the formulas for the trace. So just the sum of diagonal matrix elements of that operator in some basis. Now we know how these guys act. So that's the sum 1 to n, EI, and here Pu, and here how was it? V, EI times V, right? That's the action of the projection. Now, the Hermitian product is linear in this first term, so I can rewrite it as a sum V, EI, and here EI, Pu, V. So that I again can compute EI, and here I can compute it like this, right? UV times V. And finally, I obtain the Hermitian product of U and V times sum from 1 to n VEI EI U. And now, since this is an orthonormal basis, this is just a Hermitian product of V and U. So this is UV times VU. And by the by the complex conjugation property, this is the same as absolute value of UV squared. So that's the formula that we already saw last time, and now we see it again. So that's the probability to measure 1 in the state PV for the observable PU. And this means that if you start with this state and you want to measure what's the probability to find your system in the state PU, so then that's this formula. So how is it? Tell me, okay, now we spent a couple of minutes on doing first-year linear algebra. Is it okay if I do it from time to time? It's, I think, okay, of course, you can probably do it better than I do, but is it okay if from time to time I do elementary things? Okay, good. So that's what I wanted to tell you from the last time. There is this kind of double interpretation of orthogonal projections. And this formula is a very, very elementary formula, but in quantum theory and quantum physics, so on the physics side, this is one of the greatest formulas, right? So this formula has whatever, huge applications in physics. So now I want to turn to a somewhat more mathematical aspect of the theorem. So let me copy again. I erased it, but I should not have erased it. So let me say again that observables A are self-adjoint operators. Now let's do a simple thing. Let's consider the imaginary unit times that space. So in fact, what are these guys? So if I multiply self-adjoint operators by imaginary unit, so their self-adjoint property will be lost. Instead, it will be replaced by the property that they are anti-self-adjoint. So those anti-self-adjoint operators, they have an interesting property. So they form something which is called the Lie algebra on the commutator. So as usual here, I probably have to ask you, who of you doesn't know what is a Lie algebra? Okay, so it's absolutely no problem. I'll tell you the definition. So first of all, so let me recall that the commutator of matrices is defined simply as B1, B2 minus B2, B1. Now, the first statement in this fact is as follows. So this commutator preserves this space IA. So indeed, suppose B1 and B2 are in IA. So then if you apply a Hermitian conjugation to this commutator, what will happen? So you will have B1, B2 minus B2, B1 star. Recall star changes the order in the product. So you will get B2 star, B1 star minus B1 star, B2 star. Now, by this property, star changes the sign. But since there are two factors in each of the terms, it changes sign twice. So we get B2, B1 minus B1, B2. And this is exactly minus the commutator of B1 and B2. So that's the first property. There is something which is called the Lie bracket. So it takes two of those operators and it gives the third one, which is just a commutator. So two more properties that one needs to verify. So the first property is that B1, B2 is equal to minus B2, B1. Which is also known as skew symmetry. So this is completely obvious, right? That's just because the commutator is made like that. So the third property, probably most of you have seen it. It says the following. Take a double commutator, B1, with commutator B2, B3, and now take a sum of three terms like that, which are cyclical in 1, 2, 3. So 1, 2, 3, 3, 1, 2, 2, 3, 1. So there will be three terms. So this sum must be 0. And this is called the Jacobi identity. I guess most of you at some point in your either linear algebra or quantum mechanics or somewhere, you probably checked that actually it works. Those of you who never checked it, please do it as a small homework. So you just should open all those commutators and you will get how many? 2, 4, 12 terms, right? 12 terms, and all those 12 terms should cancel each other. So now, one example and a couple of observations. So remember last time our favorite example was the story with a Hilbert space equal to C2. And then we introduced the three Pauli matrices, which were elements of A. So they're observables. Now, so they're observable, so they don't form a Lie algebra. However, you see this notation indicates that it's actually easy to turn them into generators of a Lie algebra. So let's consider, for instance, the following combinations. For whatever historic reasons or for physical reasons, I divide them by 2, but doesn't matter. So I multiply each of them by I, and I divide by 2. Well, now for 2 of them, one can ask, what will be the commutator? So someone knows the answer by heart.
So delta AB plus something.
No, not delta.
No delta AB. The experts make a mistake here. Okay, let me write the answer. And I think actually the answer, I tried to compute it correctly, but well, I hope I did compute it correctly, but still you need to check. You need to check my computations usually. I think it will be something like this. And my hesitation is about this minus sign. We come back to discussing it. So you see, this is a sum over C of some quantity epsilon ABC that I should explain now, and times the similar generator I sigma C over 2. So I get from this I over 2 of a Pauli matrix, if I take a commutator, I get again I over 2 of a Pauli matrix. Now what is epsilon ABC? So it's equal to plus 1 if ABC is a positive permutation of 1 to 3. permutation of 1 to 3 is equal to -1 if A, B, C is a negative permutation of 1 to 3 and 0 otherwise. So what does it mean otherwise? If it's not a permutation of 1 to 3, this means that ABC has repeating indices, right? If it has repeating indices, it's 0. If it is 1 to 3, 3, 1, 2, and 2, 3, 1, it's +1. And if these are the other 3 permutations of 1 to 3, the negative ones, then it is -1. So for instance, I claim this, and so on. So why I was hesitant with the minus sign, why don't I remember it by heart in such a standard example? That's because, you see, this transition from observables to elements of a Lie algebra is somewhat arbitrary, right? So yes, I should multiply by I should divide by 2 for some whatever historical or physical reasons. But for instance, I could have added here minus signs, right? That would also be elements of the Lie algebra. And note that if I add minus signs everywhere, minus sign here, minus sign here, minus sign here, the sign here will change, right? Because on the left there will be 2 minus signs, and on the right there will be only 1. So in principle, if I do this, then this minus sign will disappear. Maybe one notational remark. Some of you probably know it, but for those of you who don't know, so this is called, so this Lie algebra has a special name, and it's a kind of funny name, SU2, so special unitary of dimension 2. At the moment it doesn't matter for us too much, but so that's an interesting example. Now, a remark. Well, I said that the commutator preserves IA. So you take a commutator of 2 elements of IA, you get an element of IA. But now what about observables? We'll see that IA also plays a big role in this theory, but what about observables themselves? So 2 facts. Let me write it in the following way, and you tell me whether it's understandable. So what does it mean? So if I take a commutator of an element of IA and an element of A, of an observable, I get again an observable. So that's what these notations say. Now, I'm not going to check it again, but please check it. So that's an easy fact. So you can produce new observables by taking commutators with elements of IA. Finally, from time to time, and actually at the next hour, we'll have to take commutators of observables as well. In general, this does not make that much sense. However, if one checks the formulas, it turns out that the commutator of 2 observables is sitting in IA. Okay. So that's a new and interesting structure. So we'll make use of this structure quite a lot. But maybe now what I want to do, I want to formulate some quite fundamental theorem. If I'm not mistaken, that's probably the first statement that we call a theorem in this course. Of course, one should take a little bit with a grain of salt. And as I said in the beginning, this is not quite the standard math course, right? So up to now, we didn't have really kind of statements that we prove. Okay, let's try. So this theorem is called the Heisenberg's uncertainty relation. And it's formulated in the following way. So suppose let me call them A1 and A2. I wanted to call them A and B, but now B I denoted the elements of IA. So, all right. So let's say we have A1 and A2, two observables. And then we have M, the state. So then there is the following inequality. I'll write it down and then I recall the notation. So the variance or the square of the standard deviation of A1, that's all in the state M, times the variance of A2 in the same state M is bounded from below by 1/4 absolute value of trace of M times the commutator of A and B squared. You see, so that's a very, very interesting inequality. But maybe first a kind of formal remark. On the right-hand side, remember we had this discussion of the commutators just some minutes ago, and the commutator. Oh, sorry. Yeah, that's what happens when you change notation on the way. So, so that's a commutator of A1 and A2. So this guy, strictly speaking, is not an observable, right? This commutator of A1 and A2. In principle, if you multiply it by I, then it becomes observable. So you can, if you want, put here an I or minus I. And then, of course, since you have an absolute value here anyways, so the situation does not change. Right. Okay. So now let me give you a proof, and maybe in the course of the proof I also remind you what these things are. So the proof starts with the following remark, and maybe if I'm not mistaken, I don't quite remember. Donald, could you recall me? So this is a statement of one of the exercises, but for today or for the next day. So the claim is, say, if A and B are Hermitian, and positive, then their trace is non-negative.
Yeah, for next one.
So this is So that's on the problem set 3, right? So for this reason, I'm not going to prove it. Especially, I think it's actually homework. Right, so you prove it. But we assume that it's true. So you take a trace of a product of two positive self-adjoint operators, you get some number which is non-negative. Now, another remark. Suppose you take any operator. So then, which one I want? Then the operator x star x is self-adjoint and non-negative. So why is it the case? Well, self-adjoint is just trivial. So I take a Hermitian adjoint of this x star x. I guess x star times x star star. But since Hermitian conjugation is an involution, I get x star x. Now, why is it positive? So that's because if I take some vector u and I consider the action of x star x on u and the Hermitian product with u, then I can use the definition of the adjoint operator and bring x here. So this will be the same as xq xu. And this is square of the norm of xu. And this is non-negative. All right. So now I do the following. So I consider a real parameter S, and I construct the following function of this real parameter S. This is a trace of A1 plus IS A2 star times A1 plus IS A2 times M. So note that here what I have a trace of a star of an operator times this operator times M. Now, by this remark that I gave you before, this factor is actually a positive or non-negative Hermitian operator, right? So this guy is a non-negative Hermitian operator. M is a state, and by definition, M is non-negative, right? So this means that by this exercise that you're supposed to solve for next time, this combination is always non-negative. Now, let's open the brackets. Let's apply this star. So all in all, we have the following. Let's apply the star. We get A1 star minus IS A2 star times A1 plus IS A2 times M. Now recall that A1 and A2 are observables. So this means actually I can forget those stars if I want. Now what we get? We get trace A1 squared times m. Now here will be minus and minus from the product of two i's plus s square trace A2 square times m. And so what do we get here? Plus is trace A1 A2 minus A2 A1 times m. Is it correct? So it was A1 A2 minus A2 A1. Okay. Now maybe it's better to put this I inside here, because recall then, so this commutator is anti-self-adjoint. If you multiply by I, it becomes self-adjoint, and then this trace becomes real. So in fact, what we have here, this function of s is a quadratic polynomial with real coefficients. And it's always greater or equal to 0. Then from, is it like high school or secondary school, right? So then we know that there is the following inequality. Right? So this should be greater or equal than 1/4 of the square of this linear coefficient, right? So that's just because it's a quadratic polynomial. All right, so now the right-hand side is fine. What about the left-hand side? So that's actually the inequality that we get. Now, let me recall. So now we still need to get the inequality from the Heisenberg's uncertainty relation. And the inequality from the Heisenberg's uncertainty relation, so the variance of A, I don't quite remember, how did we denote it? So in the state M, right, or sigma A squared, what is it? So one possible definition would be the trace of A minus A bar squared times M. That's just for the probability theory, the definition of the variance. And A bar is just a number, trace of AM, the mean value of our quantum observable A in the state M. So that's the definition. So now we want to replace the left-hand side of our inequality by this left-hand side. So those two left-hand sides are not quite the same, right? Now what do we do?
Just subtract from A1.
Right. So so in fact what we do, so let's call this star. So U star for A1 tilde equal to A1 minus A1 bar. A1 bar is just a number. And when I write A1 bar, I mean the unit operator proportional to A1 bar. So A2 bar equal to A2 minus A2 bar. And observe that the commutator of A1 tilde A2 tilde is simply equal to the commutator of A1 and A2. That's because you subtract something proportional to 1, commutator of 1 with anything is 0. So this means that the commutator doesn't change. Now, once you replaced A1 with A1 bar, this becomes sigma A1 squared. This becomes sigma A2 squared. And this guy doesn't change. So therefore, we get the Heisenberg's uncertainty relation theorem.
There is one false. Yes.
Oh. I think this means that the correct one was 1/4, right? You're right. Actually, I don't quite know. In my notes, it is 1/4. I don't know how this 1/2 got there. And of course, the correct one is 1/4. If you take a square root of it, you will get 1/2. All right, so let's have a break and then we discuss a little bit more. We'll spend more time with the Heisenberg uncertainty. We'll get back to it. But yeah, so probably it's a good time to stop and have a break. Okay, so this inequality, what does it say? It says that potentially if the commutator is non-vanishing, then of course still depending on the state, but potentially the product of variances cannot be 0. Perhaps one small comment about it. So what happens if the commutator is 0? So we remark. So assume that the commutator is 0. Well, first of all, the theorem, the Heisenberg's uncertainty, at this point says nothing, right? Because the right-hand side is 0, the left-hand side is the product of two positive quantities. Well, I mean, it's trivially satisfied, so nothing happens. But actually, we know a lot more. Suppose you have two self-adjoint operators which commute. Then you probably know from linear algebra, I guess, do you? So that they can be, how it's called, simultaneously diagonalized, right? So in other words, maybe I write a somewhat more abstract formula. So so there are eigenvalues lambda 1, lambda n, and here possibly with repetitions. And similarly, there are eigenvalues mu1, mu_n. There is E1, En. an orthonormal basis of H such that A1 admits the spectral decomposition lambda sum over lambda I pi, and A2 admits the spectral decomposition mu I pi, where pi is a projector on EI. Or if we write it in matrices, right? So we now have a basis and we can write it in matrices. So A1 will be represented by a diagonal matrix lambda 1, lambda n, and A2 will be represented by a diagonal matrix mu1, mu n. So that we know from linear algebra. I don't know whether it was in your linear algebra course. If not, look it up. So now let me recall that if we have an observable and we choose a state which corresponds to an eigenvector of the observable, so then in this eigenstate the variance is 0, right? So that's because if we measure it, we get the corresponding eigenvalue. Now, these two observables, they have lots of common eigenvectors. So all the EIs are common eigenvectors. So this means for every projector Pi, we have sigma A1 equal to sigma A2 equals 0, right? So in this state, there is no uncertainty. There is no probability theory. So in the state I, A1 is equal to lambda I, and A2 is equal to mu I. No uncertainty. The standard deviation is 0. The variance is 0. So the left-hand side is actually 0. Not only it may be 0 because we don't have an estimate, but actually in those states it is exactly 0. So we'll return to those observables which have vanishing commutators a bit later. But now I want to present you the last axiom. Remember, we started last time with some axioms which introduced observables and states and measurements. And now that's the last axiom. So quantum mechanics actually introduces for you a dynamical system. So axiom A5 let's call it quantum dynamics. So this quantum dynamics comes in two different forms. We'll start with one of them. So first of all, this axiom says that there is a distinguished observable called the Hamiltonian of the system. And let me first define this dynamical system or the quantum evolution in the so-called Schrödinger picture. We'll see now what this means. So it says the following, that there is a differential equation or ordinary differential equation on this space of states S, and this differential equation looks as follows. We now say that the state depends on a parameter. This parameter is called time. And the right-hand side, again, I shouldn't kind of screw it with the signs. Looks as follows. So this is minus I times the commutator of this observable H with the state. And well, this is the so-called Planck constant. To be honest, for us, in a mathematical theory, it is somewhat optional. So there are different approaches that we can take to it. Of course, in physics, that's a very important constant. So what we can do, we can think that this is simply a positive real number. So that's one approach. So one possible choice for it would be to put this positive real number to be equal to 1. Right? That's one possibility. So another possibility to keep it as a positive real number. One possibility that we perhaps explore later on is to treat H as an indeterminate or as a formal parameter. So we can actually study the dependence of our dynamical system on this H bar. Of course, in physics, this H bar is actually a positive real number which has a concrete value. But we don't care so much. Right. So this is a very, very simple differential equation. Perhaps I should add the following. So recall that among the states, we have those so-called pure states, right? So we have pure states, which are defined by projections, and projections defined by unit vectors. Now you may actually ask what would be the evolution, what would be the dynamics of that unit vector. So this is a version of the axiom 5. You can actually, instead of imposing this condition, you can impose the following condition. You can say that the unit vector which defines a pure state depends on t, and is defined by this differential equation. So now H is an operator acting on the vector. So that's another form of the same axiom. So as experts in linear algebra, what's your feeling? Are these two statements equivalent? Suppose that I restrict myself here to pure states. So are they equivalent? What's your guess?
They should be.
They better be. But I think linear algebraically, it's more or less obvious they're not. Why? I think you will have a rather easy time to show that if U evolves like this, then the corresponding pure state Pu will evolve like that. So that's an easy task. However, the other way around, I have doubts, and that's for the following reason. Suppose you add to your Hamiltonian, suppose you add some constant times a unit operator. So what's going to happen? So here, strictly nothing going to happen because in the commutator, this term will die. So here, there will be consequences. For sure, when I do this, the evolution of the unit of this unit vector changes. So in fact, it's not going to work the other way around. But remember, maybe you forgot, or maybe you didn't forget. Last time I told you that actually those unit vectors, they are not quite states, right? You should divide them by an equivalence relation. And the equivalence relation is multiplied by some complex number with absolute value equal to 1. And actually what's going to happen here, if you add to this operator some constant times 1, so then it will turn out that eventually it will change U by such an overall phase. And anyways, you're supposed to consider those U's modulo this equivalence relation. So it changes U modulo equivalence relation. But still, just I wanted to tell you, we're going to use those equations as if they were equivalent. But maybe from time to time, it's good to remember that strictly speaking, they are not completely equivalent. And that it's very convenient. Most people, like whatever, 99% of people doing quantum mechanics work with this equation. It's relatively rarely that people work with that equation. So, but this equation is conceptually correct. This equation is slightly conceptually incorrect. Slightly. But again, so usually when people say a time-dependent Schrödinger equation, so they mean this. Right. Okay. So now I would like to make a small linear algebraic digression. I want to say one of the last ones in the course, but you never know, right? So one small digression that you probably all familiar with, or maybe not, but just to make sure. I would like to recall the following. Suppose we have an operator on H. H is finite dimensional, and the operator is not necessarily self-adjoint, anything. So then one can define the exponential function of this operator just by the standard series for the exponential. Now, this series is actually absolutely convergent for all A. By the way, for matrices or for operators, what does it mean absolutely convergent? Just to check. Absolutely convergent under, yeah, say for instance, whatever, after all, the space of matrices is a finite dimensional space. All norms on that space are equivalent, so whatever, operator norm, any other reasonable norm that you can invent. So it's absolutely convergent, and it has the following properties. I'll list some of them. Of course, exponential of 0 is the unit matrix or unit operator, identity operator. Exponential of a Hermitian conjugate, exponential of the adjoint. Is the adjoint of the exponential. Exponential of a conjugate, where G is an invertible operator. Is a conjugate of the exponential. Exponential of minus the operator is the inverse operator of the exponential, and maybe something which so I take two parameters and take exponentials of A times those parameters. Well, as a good exponential, simply those things add up. So, does it all look familiar? Nobody concerned about it? All right, maybe still one remark. So all this holds true. However, as you can probably imagine, if I take the product of exponentials of two operators, in general, this is not the exponential of the sum, right? So we'll talk more about it. Maybe I'll just state one formula. If we have time later on, maybe we prove it at some point. It's called the Lee-Trotter formula, and it will be of some importance for us towards the end of the course. So this formula tells you something. So there are actually, this story is a big field. So there are many things that people do in different fields of math about this relation between exponential A, exponential B, and exponential of A plus B. So it sounds as a silly linear algebra problem, but actually it's an entry to a big field. Now let me show you one of the formulas that we'll be using later in the course. And it says the following, that if you take exponential of A divided by n, and you multiplied by exponential of b divided by n, you take a power n, and you take a limit of n going to infinity. So you take a natural number n. So you first divide these things, you multiply, and then you send n to infinity. This is actually equal to exponential of a plus b. So as I say, maybe at some point we even prove it, but think about it. Think how you would prove it. That's a mix between first year calculus and first year linear algebra. So this formula is not true, but if you give a small analytic twist to it, then it becomes kind of almost true in the n to infinity limit. So why did I decide to tell you, to recall you this story? That's because we would like to solve this equation. So let's try to solve this equation. In order to do that, may I erase it? Or, okay. Because I want to keep the equations on the other blackboard. So let me recall you the definition of u of h. So these are operators on h which satisfy the rule g star times g is equal to 1. So these are unitary operators. And in particular, from this, it follows that g is invertible, right? Because we have an explicit inverse. G star is the inverse of g. Right. So now, a remark. If you have b in IA, then exponential of b is a unitary. So b is anti-self-adjoint, then exponential of b is a unitary, and that's so that's easy to see. So if we compute the adjoint of the exponential of b, this will be exponential of b star, and this is equal to exponential of minus b. And by one of the properties, that's the exponential of b to the power minus 1. Now let's define the operator u of t as the exponential of minus I over h times t. Now, for t real, for t real, it's clear that this guy, so this combination is an IA, right? Because we have real numbers and then we have this I, so it moves it to IA. And then this means that this operator is unitary. Now claim. So let me denote this equation as CH for Schrödinger. So let's take any vector u0 and let's consider u of t, this operator acting on that vector. So this gives us a family of vectors which now depend on t. And this is the unique solution of SCH with u of 0 equal to u0. So let me briefly check that this is indeed the case. So we compute the derivative, and this derivative is d over dt of this u of t times u0. But recall the properties of the exponential function, right? So when in the first year calculus you derive the derivative of the exponential function, you're basically using the property of the exponential function to be additive. Or whatever, multiplicative. Now recall that here, if you change t, so this function satisfies exactly the same property as the ordinary exponential function. You only get a very different behavior when you try to multiply exponentials with different operators there. But if you just have the same operator, so then this function behaves exactly as a function of one variable. So this means that you can differentiate this expression with respect to t and get minus 1 over h capital H. And here you will still have u of t u0. By the way, why do I write it to the left and not to the right? Minus I over h, h. Because it doesn't matter, right? Once we have just the same operator, it doesn't matter. I could have written it to the right, but I find it convenient to write it to the left. And this is equal to minus I over h, h, u of t. So this vector does satisfy this differential equation, that this is a unique solution follows by the uniqueness of solutions of ODEs, with constant coefficients. Right. You probably don't need this motivation, but for me it's difficult not to say it. You know, when I teach the first year linear algebra and I have to motivate why do we want to do whatever those unitary operators, why do we want to study it, I say the following words. See, so this Schrödinger equation, it's an equation which describes any quantum system, right? Of course, we said that that the Hilbert space was finite dimensional, but let's for a moment ignore it. Let's say, for instance, our quantum system is the universe. Now, that's the equation which describes the evolution of the universe. Just this H is some very, very huge operator acting on some very, very big space, but otherwise, that's this equation. And note, this is the solution of this equation, right? It's already sufficiently surprising to write in one line an equation which describes the evolution of the universe. I find it even more intriguing and surprising that here is just this very simple solution, so which contains all the information on what happens everywhere, in particular in this room, and so on. Of course, here, I mean, we're cheating somewhere, right? Still, there is also some truth in what we're saying. So those very simple-minded Lie algebra formulas that we are writing now, they are kind of important, and they have some kind of ambition in them. All right. Now maybe somewhat less ambitious words, somewhat more technical. So this operator, it's called the evolution operator. Maybe one more word here. So another word or another name for this observable is the energy. And in particular, usually we were denoting the eigenvalues of our operators by lambdas. But the traditional notation for the eigenvalues of H is the letter E, because that's the energy. At least these are the words that we are supposed to say on the physics side. All right. So now I would like to introduce another picture. As I said, the axiom 5 comes in some way in two versions. I already introduced the one version and then the other version, but now there will be an entirely different version which is in some way equivalent. So the dynamical system that we introduced in the Schrödinger picture is saying that the state of the system evolves with time. Maybe let me, before doing that, let me make one more remark. We solved the Schrödinger equation for the pure state, for the unit vector. We can also easily solve the Schrödinger equation for the generic state m of t. And the solution will be now u of t m naught u of t inverse is a solution with m of 0 equal to m naught. So this simply follows from solution of this equation. So vectors get multiplied by u of t, states get conjugated by u of t. Now, A5 tilde which is called the Heisenberg picture. We're not going to use it very often. You will see why we want to have it. So in the Heisenberg picture, the dynamical system is organized differently. Instead of saying that the states evolve, we say in a bit strange way that the states are always the same. However, what happens that's the operators or observables evolve. So you fix the state of your system once and for all, and you say that the observables that change with time. There is, of course, in some way also some intuitive meaning into that, because, I don't know, in classical mechanics, imagine you have that chalk, and the observable is a position of that chalk, and now the chalk moves. So the position changes. So I guess that's how people were thinking about it. But whatever it is, for us, it's simply, remember, our quantum system has two pieces in a description: observables that we can measure and the state. We measure them in some state. Now, in the Schrödinger picture, we are saying that the state evolves with time according to this law. And in the Heisenberg picture, the states do not evolve with time. However, what evolves with time are observables. Now, a simple fact is as follows. So suppose we consider the mean value of A, which is equal to a trace of AM. So that's something that we supposedly can observe. Now, in the Schrödinger picture, this is a trace of A, let's call it A0, times M of t. The observable never changes. But in the Heisenberg picture, this is A of t times M0. Now, let me substitute here this solution of the Schrödinger equation. So recall that M of t gets conjugated, right? Now, can you guess the solution of the equation for A of t? Right? It's a very similar equation where we change the sign, right? Now, if we change the sign, this means that here we'll have to replace u of t by u of t inverse, right? In the solution. Now, notice that these two equations are simply equal to each other. Right? Because you can, under the trace, you can move this u of t minus 1 to here. So that's called the equivalence between the Schrödinger and the Heisenberg picture. In fact, we're not going to use that much the Heisenberg picture, but I wanted to show this remark to you because, first of all, that's one of the simple and fundamental statements in mathematical quantum mechanics, and also because it motivates for you an interesting definition. So A in IA is a, well, here there are different names. Is a conserved quantity. Or sometimes people say quantum integral if the commutator of H and A vanishes. Now we know why this is an interesting consideration. That's because in the Heisenberg picture, the corresponding operator doesn't change. It's also because if you take the time derivative of the mean value in whatever picture you want, right? The two pictures are equivalent. You will get 0. In particular, let's do it in the Schrödinger picture, because that's the picture that we kind of like. Right, so that's what the original axiom A5 was saying. And now under the trace, you can bring the commutator on A. And this is equal to 0. So I think we'll stop here for today, and next time we'll try to explore more of this situation of what happens with those conserved quantities or quantum integrals of motion. Okay, well, that's it for today.